Elasticity is the property to restore the natural shape of a body after deforming forces are removed. There are different types of bodies. Some are more elastic, some are less elastic. Opposite to the word elastic is plastic. So something that is less elastic is more plastic, you can say. In fact, when we say a body is plastic, it means that when you deform it, it remains in that deformed state. It does not even try to come back by slight amount. Inelastic word is also used to represent plastic behavior. Elastic is opposite to plastic or inelastic. The reason for elasticity is, of course, interparticle forces that are electromagnetic in nature. We will now talk about stress. There are different types of stress. So let's understand different types. This is some body on which many forces may be acting. Right, left, up, down, even at different angles. But let's say that the net force is zero. Net force is zero. So if you want to look at the simple way, you can only think about one force to the right and one equal force but to the left. That's it. But actually there can be many more forces. The basic thing is that the total of all forces must be zero so that the center of mass does not accelerate. If you think about only two forces to make it look simple, one to the right, one to the left, equal in magnitude, then fine. But it will be a special case then. Now, imagine some boy is standing and his right hand is pulled by somebody, left hand is also pulled by somebody, and let's say these two forces are equal in magnitude. They are opposite in direction and equal in magnitude. So naturally the center of mass of the boy will not move, but the boy will cry. So equal and opposite forces may get cancelled for the whole system. But within the system, what happens? Within the system, stresses are developed. So the boy cries because of stresses getting developed inside his body. Okay, now let's make it mathematically clear, and for that we will consider general case, many forces acting, net of all is zero. Consider any cross-sectional area, but to make it general I won't take it like this, I won't take it parallel to this surface. Let me make it somewhat general. So how about this area? Let's say that area is delta S. Okay, so there are two sides of that area, left side, right side. These two parts will apply equal and opposite forces on each other. Okay? Suppose this force is on one part, then that force would be on the other part. Well, direction would depend on how other forces are acting. We break this force in two directions, one parallel to this surface and other one parallel to this surface, perpendicular to this surface. One parallel to that delta S, other perpendicular to delta S. Perpendicular one I can denote by normal, Fn. Parallel to the surface I can denote by either this or by writing tangential, T for tangential. Then perpendicular force upon area, this is called longitudinal stress. This is defined as longitudinal stress. And F tangential by area, that is called or defined as shear stress. Now it depends how other forces are present. Sometimes there may be a tendency for this shape to get longer, to become longer. Sometimes there can be a tendency to shrink. So accordingly these forces will change their directions. If there is a tendency to become longer, then longitudinal stress is called tensile stress. If there is a tendency to become longer, then longitudinal stress is called tensile stress. Here this will become longer. And if there is a tendency to compress, then the same definition for LS, longitudinal stress, will also be called compressive stress. So longitudinal stress itself becomes tensile stress or compressive stress, depending on the situation, whether it is elongation or it is compression. If nothing is said about area, it is taken for granted that it is perpendicular to, or it is parallel to the surface. If nothing is mentioned about area, it is taken that area is parallel to the surface or perpendicular to the length. So that was about two types of stresses, longitudinal and shearing, and longitudinal itself could be called tensile or compressive. Then we have volume stress. Imagine some solid inside some liquid. Imagine some solid inside the liquid. And we will assume same pressure. Then this pressure P, if it is P, that itself is called volume stress. There is alternative mathematical expression also. For that you need forces. Imagine various forces acting. Liquid will apply forces on the solid. Normal forces, perpendicular at various points. F divided by area under consideration, that is also volume stress, and F upon area is pressure. So we talked about three types of stress. Likewise, we have three types of strain. Strain talks about how much is the deformation per unit. How much is the deformation per unit? That's what the concept of strain talks about. For example, if it is longitudinal strain, then how much is the change in length per unit length? How much is the change in length per unit length? So we can have elongation, we can have compression, and likewise for elongation we have tensile strain where delta L is positive. For compression, when delta L is negative, we have compressive strain. For this case, a solid is experiencing pressure from all sides or experiencing force from all sides. It shrinks. Well, actually it can become bulky also. Suppose, for example, there is a balloon. Or let me say some sponge object which is inside some system which has high pressure from outside. Now you release the pressure from outside, so it expands. So volume strain is delta V by V, change in volume by volume. Shearing strain. Shearing stress has to do with tangential force. So shearing strain must be related to tangential deformation. Tangential deformation. There is a nice figure to understand tangential deformation. It should appear on the screen any moment. See that a fat book, you are pushing it in this manner. You can very well imagine what will happen to the book. This side will move to the front, base will remain where it was. So suppose X is the deformation. The top was aligned with the bottom, but now suppose top slides by X unit distance. H is the distance between the parallel surfaces, top and the bottom. So this surface is shifting by how much? X. And what is the distance between the parallel surfaces? H. Okay, this is called shearing strain or shear. This is called shearing strain or shear. Coming to Hooke's law. Hooke's law is about, yes, go ahead.
Sir, here what is X?
Can you repeat?
Sir, here what is X?
X is the deformation. Suppose this is the bottom surface, this is the top surface. Okay. Initially, book is like this. These two, you can very well imagine that this is joint, this is joint. Now this glides to the right. So by how much distance does it glide to the right? That is X. Okay. Hooke's law is about longitudinal deformation. And longitudinal means both tensile or compressive. If it is tensile stress, tensile strain. If it is compressive stress, then we have compressive strain. It says that the ratio of the two, stress to strain ratio, longitudinal, both longitudinal, that is either both tensile or both compressive. That ratio, stress is to strain, is constant. And that constant is denoted by Y, Young's modulus. And this Young's modulus depends on the material. For a particular material, the ratio of stress to strain is constant. Okay? But this law is workable for small deformation. Okay, it is applicable for small deformation. Now, we are saying stress upon strain, longitudinal both. Since it is longitudinal, area will be the cross-sectional area. That's it. Okay, FL by A delta L. Let me use capital L. So just like we talk about longitudinal stress upon longitudinal strain, longitudinal stress upon longitudinal strain, and we call that ratio as Young's modulus for elasticity. We can also talk about other ratios, other stress, other strain. When we talk about shear stress, shear strain type of thing, okay, shear stress X by H is shear strain. Shearing stress. Shearing strain is X by H. So FH by AX. This is called shear modulus eta. Shear modulus eta. Okay? And when we talk about the volume, that is volume stress, volume strain ratio, you are familiar, I mean you have seen it in sound topic in action. Regarding strain, it is delta V by V. Regarding stress, there are two approaches that are used. Okay? In one case, it is the pressure. And in the other case, it is change in pressure. And we want positive answer, and delta V can be plus or minus. In fact, here also we want positive answer. In fact, if you put mod over what is changing, that's enough. Delta V, if you put mod over here, others are anyway positive. Here, delta L, if you put mod over delta L, it's enough. I think I will just remove it and say that make it positive. That's it. Make it positive. Now, since if you increase the pressure, volume should decrease. If delta P is positive, delta V has got to be negative. So it's pretty obvious that minus has to come here. And for others, you have to keep in mind that answer has got to be positive. These are all positive things. Y, eta, B. Now regarding this point, why are we talking about these two? Why are they different? I mean, what's the reason for talking like this? You see, sometimes you are interested in the change in pressure because pressure is already there. In case of sound, we would talk about delta P because when you speak, you're not, I mean 1 atm is anyway there. 1 atm pressure is anyway there. So when you speak, 1 atm can become 1 plus something, little number, or 1 minus something. Why should we be concerned with absolute value of pressure? When sound is progressing, it is a pressure change we are interested in. It is delta P that is of interest there. Right? So in some circumstances, pressure is already there due to atmosphere. We are just interested in the change taking place in the pressure. So we could use this. Okay, that's why there are two ways to consider this or that, depending on the situation. So this is called shear modulus. This is called bulk modulus. And all are positive. Yes, yes, go ahead.
Sir, I didn't understand how that strain is X by H in the second case.
Can you repeat? How?
In the question in that book, how strain is X by H?
This one?
Yes, sir. How it is X by H? How it is X by H? Strain.
It is defined like that. It is defined like that. That's the definition. Change in this, how much is it sliding divided by this distance. That's how it is defined. That's it. Okay? Now if you make a wire, yes, go ahead.
No, sir, but why can't we define delta L by L? No, sir, like that, why can't we use delta L by L in this case also? Like change in the initial dimension by change in dimension. Why can't we use that formula here?
So which length will you take? Which length will you take?
No, sir, X is changing now, sir. So horizontal component is changing, so we are taking the horizontal component.
Which L will you take is my question. Which L will you take? From this to this, that L you will take? This L from here to here?
Yes, sir. Horizontal components only changing. So we can take that as a length.
Okay, you are saying this can be taken as length. So if this is L, then you are saying how about X by L? Well, that's because it is relative motion between the two surfaces. It is the relative motion between the two surfaces that is considered here. When we take delta L, you have a rod like this, and that rod itself becomes like that. This rod itself becomes like that. Here it is the relative movement between these two that we are talking about. If you define it as X by L, you are dealing with only one fellow. But it is about relative shift that is taking place. Okay, here it is the change that is taking place in L. So L is taken here. Here it is not change that is taking place in L. It is shifting with respect to this. So the two surfaces are involved. That is why. Now if you change the length, say for example you want to make a wire longer, then it will become thinner. If I make it longer, it will become thinner. If I make it shorter, it will become fatter. So we have a concept called Poisson's ratio. And this Poisson's ratio is defined as change in D upon D divided by change in length upon length. Now since if delta L is plus, then delta D has got to be minus, and Poisson's ratio is taken as positive. Delta L and delta D will always have opposite signs, so we have a minus sign here. That's the definition of Poisson's ratio. And just like different materials have different Y, different materials have different eta, different B. They also have different sigma, Poisson's ratio. Sigma, of course, will have no unit. Earlier I talked about bulk modulus. 1 upon bulk modulus is called compressibility. The compressibility is simply 1 upon bulk modulus. Okay? So these were some definitions and some concepts. Now, stress will be tension upon cross-sectional area tension is equal to the weight of the load just work it out. Don't use the unit Pascal here. Generally speaking, Strain has no unit. Strain is delta L by L. Unit for L is meter, so delta L will be in meter. It's the same tension. Area is also the same. One is the answer to part A. So strain in copper wire divided by strain in steel wire is 2 by 1.3 or 20 by 13. Any questions or we proceed further? Can you complete this and let me know the answer?
About 8 Newton per meter square.
So 5 into 10 power 5 into 10 5 into 10 power 7
5 into 10 to the power. What was the first answer? Shall we hear answer?
So 10 raised to power 8.
10 raised to the power 8 is right. Newton per meter square. Any problem? Let me know. Actually, it seems to be formula-based question. Everything is given straight away.
Yes sir, I am also getting 10 power 8 Newton per meter square.
Fine. We stop at this point.